Okay, so before I do this lesson, I always start with kind of two preambles. First one, I've been kind of lying to you guys for the last 3 weeks. I do this a lot. Sometimes I tell you a partial truth because we weren't quite ready for the whole picture. Okay. Previously, I told you that things that were strong because they conduct well, and things that were weak because they didn't conduct well. That's actually not true. Well, it's kind of true. But sometimes I find when I'm teaching courses, sometimes it's better for me to tell you kind of like part of the truth until we've learned more content. And now that I've taught you some other things, now I can give you a better explanation of strong and weak. Okay, so I want to start with apology. I do this a lot of times here. But I need to actually change your definitions of strong and weak. It's not based on conductivity, it's actually based on percent ionization. Okay, I'm actually going to write that down here. Strong and weak is actually based on what we would call a percent of ionization. And I'll show you what I mean in a second. I-O-N-I-Z-A-T-I-O-N. Okay. Let me read off my slide here. I don't do this a lot, but I'm going to read off this first slide here. Acids and base vary in strength from very strong to very weak. And you guys will remember that this is different than concentration. If I give you something that is concentrate or dilute, you guys recall that those words are not the same as strong and weak. Okay. But I kind of lied to you. I told you that strength is determined by how well a solution conducts electricity. That's actually not entirely true. Here's actually the truth. It's more accurate to say that how well a solution conducts depends on its strength, which seems kind of backwards because you're like, hang on, Chris, doesn't that say the same thing? But let me see if I can try to explain this here. It's not that strength depends on whether it conducts or not. It's the fact that because it's strong or weak, that's actually why it conducts or doesn't conduct. It actually kind of needs to be thought of the other way around. A doesn't lead to B. It's more that B leads to A. Does that make sense at all? It's better to say this. Conductivity is actually a property of strength, okay, as opposed to strength being a property of conductivity. I know that almost sounds like the same thing, but there's a subtle distinction. Let me try to explain it better on my next slides here. Okay. Strong acids, what we've discovered is that their percentage of ionizing is very high. Okay. Now, this is kind of a new concept to you guys. I leave it till the very last lesson because it's a bit foreign. When we have a chemical reaction, we normally assume that all of A and all of B turn into all of C and all of D. We assume that 100% of this stuff turns into this stuff right here. That's normally an assumption we've had so far, but that's not actually true. Sometimes what happens is about half of our A and half of our B turn into C and D. And so what ends up happening when you're done is you had a whole bunch of this and none of this to start. And then slowly but surely, this stuff changes into this stuff. And we assume that by the time we're done, there's nothing left here because it's all over here. Does that make sense? But that's actually not true. A lot of times, about half of this turns into this. And what you're really left with when you're done is you're left with some A, some B, some C, and some D. Does that example make sense? Right. If I were to do it with like a manipulative here, it's kind of silly, but let me just use some sheets of paper. Okay, here's our reactants. Normally what we assume is that our reactants react together and they cease to be reactants and they become products. And when you're done, there's no reactants left and all we have is products. Okay. But that's not actually how things always work. Sometimes, of all of our reactants, half of them react and make products, but you still have some reactants left over. Let me give you a typical example. Rusting. Right. Let's say that you have a piece of iron that rusts. Does the entire piece of iron rust always? Well, sometimes only part of it rusts, right? Like the outside rusts. And then the rest of it remains. And so if you were to look at it as a percentage, you might say that like 30% of the iron rusted, but that would mean that 70% of it didn't rust. And so the word we sometimes use is quantitative. We assume that reactions are quantitative, meaning that everything here turns into a product, but that's not always true. Okay. Does that make sense what I'm suggesting so far? Well, that percent ionization really applies to acids then. Because remember, acids ionize. So sometimes what we'll do is we'll write a percentage on top of our arrow sign. And that percentage is what tells us how often our reaction occurs. So New definition. Strong things ionize all the time. That's actually the definition of strong and weak. I've been lying to you. Strong things aren't strong because they conduct, and weak things aren't weak because they don't conduct. The fact is that strong things conduct because they always ionize, and because they always ionize, then they conduct. Do you guys get the slight difference here? I'll say that one more time. Strong things aren't strong because they conduct. Strong things are strong because they always react. They always ionize all the time. And in doing so, because they're always ions, then they conduct. But what I did is I kind of told you a half-truth. I kind of skipped the middle step. So now I'm going to go back and try to fix that middle step. So this example of hydrochloric acid, I found this picture. I like this one here. It kind of illustrates the point I want to make. Here you've got hydrogen and chlorine, hydrogen and chlorine, hydrogen and chlorine, hydrogen and chlorine. This would be a neutral molecule. Should this thing conduct right now as a reactant? No, we don't have ions. But since every single hydrogen and chlorine has now broken up into pieces, and granted, I know this isn't the Arrhenius way of doing like H3O+, but if you can imagine this definition, since every single one of these broke apart, like more than 99%, it's now considered strong, and as a byproduct, it conducts. Here's another example here of a picture that I found that I hope can illustrate it here. Here's another strong acid, and as the way of kind of illustrating it, what they've done for the legend here is they've said the acid involves two pieces together, and then I don't even care what acid it is, but hopefully you kind of get the point here. All acids should involve a proton coming off and a negative something being left over. Well, look at the strong acid. Literally every single one of these guys right here that was together as a group is now broken into pieces. Whereas in a weak acid, yes, look, this guy right here and this guy right here, they broke up. And this one right here and this one right here, they broke up. But look, this one here stuck together. This one stuck together. Does that make sense? So as a byproduct, this one here would conduct really well. Why would it conduct well? Because there's a ton of ions in the solution. This one over here would not conduct as well because only a percentage of them turned into ions. Many of them remained as original reactants. Often I use silly analogies. The silly analogy I use for this one here is couples that get together, say for like prom. I already used this one with some of you. And so it's prom season, everybody's paired off, they found a date. And so right here, everyone's found a date. However, in a strong acid, after prom season is over, everybody breaks up. So these guys broke up, these guys broke up, these guys broke up. In a strong acid, everybody is underwent a breakup. Right? And so everybody's back to being a single again in this example here, right? However, in a weak acid right here, a couple of the couples remain together, right? And so even though these ones broke up again after prom, say, this one and this one and this one and this one and this one, they're still together. It's a silly analogy, but does that help illustrate the difference between the two? So one more time to say this. Strong acids are not strong because they conduct. Strong acids are strong because they always break up. Always, 100% of the time, basically. And because they always break up, then they conduct. Weak acids are not weak because they don't conduct well. Weak acids are weak because they don't always break up. Sometimes they stick together. This one and this one and this one, they stick together. And because of that, if I compare these two solutions, this guy right here won't conduct as well because there's not as much ions. So if I want to go back to my original slide here, it's all about this. It's all about the percentage of ionization. The higher your percentage of ionizing, the more strong you are. Stronger you are. That's a better word, right? The lower your percentage, the weaker you are. So I got more pictures to kind of illustrate the same point, but hopefully I've already made it here. Hydrochloric acid is strong because literally everybody's broken up into ions. Hydrofluoric acid is considered weak because there's still some HF still stuck together. Okay, so here's the general rule. Most acids fall into one of two categories, strong or weak. Okay, there are some iffy ones, but for the most part, we're going to try to delineate this very, very separately. Strong acids ionize more than 99% of the time. And there are 6 known strong acids. I want to talk about your table again here. So if you guys have a data booklet, I've already referenced this table. There are 6 known strong acids. Okay, they're the 6 top ones on the list. They are perchloric, hydroiodic, hydrobromic, hydrochloric, sulfuric, and nitric. You guys have that in front of you? It's on pages 8 and 9. So the way this chart works is it's a ranking, but now I need to reintroduce you to this again. Can you guys see how in the last column there it says KA? Okay, we're not going to use that number yet. We will eventually. But you notice how for those first 6, it literally just says very large, and then the rest of them, it actually gives a value, and the value keeps getting smaller and smaller and smaller. Essentially, that is a correlation to the percentage. Okay, these first 6, their percentage of ionization is so large that it's 100%. Okay, I don't actually believe that these top 6 are actually in numerical order. I believe they're all considered basically the exact same strength. Like they're all more than 99%, so high that basically everything always breaks apart. Okay. Now, one thing I didn't mention here is the gray bar. You guys see how like there's the hydronium ion, which is the gray bar there? That's actually very purposeful. I want to talk about that now. These top 6 things there, they would then basically 100% of the time turn into hydronium. Because if I were to give you an example here, I'm going to go back a slide here. Actually, I'll use this one here. If I were to give you HCl, if HCl reacts with water, it would give hydronium and chlorine negative. The way this table works then is it's going to tell you in the second column what it turns into when it loses its hydrogen. So can you guys see how like HCl in the column next to it, it gives a Cl minus? That kind of tells you what the other species would be right here. Grade 9 students, please head back to class. Grade 12 students, please come down to the hangar. You guys think we can hang on for... You think we can hang on just for a few seconds here? Okay, I'm almost done. Okay, this second column that's right here, the conjugate base formula one right here, we're not going to use that terminology yet, but essentially it refers to what the other species is right here. Well, because these ones here ionize basically 100% of the time, they essentially always turn into hydronium, which is why hydronium gets to go next. And then everything further down basically refers to smaller and smaller percentages. Which thing ionizes the least then? Water. And we already knew this. How often does water ionize? 2 times in a billion, which if we were to make a percentage, 2 out of a billion is a pretty low percentage. Does that make sense? Okay, let me finish this off here. Okay, so this is kind of the key slide then. Because they don't ionize well, weak acids have lower conductivity, slower reactions, and they would actually have a higher pH technically because they produce less H3O. There's actually a question on your assignment about this. The assignment basically says, I'm giving you 2 solutions, both of which have the same initial concentration, but one of them is weaker. Well, the weaker solution then would produce less hydronium, and because it produces less hydronium, it will then be less acidic. Does that make sense? Doesn't necessarily make it less dangerous. It could. Hydrofluoric acid is still scary, but it actually ionizes less. Okay, bases. I should point this out though. Most bases are actually ionic compounds, like for example NaOH, NH4OH. Okay. Just so you're aware, ionic things dissociate almost all the time. Okay, it's really just the acids we have to worry about. Strong bases usually do this all the time. Okay, but it's acids you got to worry about as to what percentage they do. So most of the time when you write an ionic equation, we've never cared about this before. But whenever you see an arrow like this, more or less it's assumed that this is 100% unless we tell you otherwise. Okay, so unless I put a percentage over top of it, like this one right here, usually we assume that everything reacts. But hopefully you guys can agree, like not everything reacts in real life. Sometimes only half of it reacts, or 23% of it reacts. So, okay, so this is the chart I was telling you about. Basically, new way of approaching it. These ones ionize all the time, and these ones ionize a lesser percentage, from about 50% downwards. So this might be 50% of the time, 40% of the time, 30% of the time. And one day in the future, I'll show you guys what these numbers right here mean, because they can actually tell you how often they ionize. Well, hydronium would still be 100% because all of these guys right here, completely turn into hydronium, which is actually why this number right here is 1. But everything below hydronium is going to be 50% or lower ionization. And eventually I'll show you how these numbers right here can be used to calculate that percentage. Okay, cool. Last topic, then I'm done. I'm going to skip to this slide right here. The last word I need you guys to know is something called a polyprotic substance. Okay. It actually makes exact sense like you think the word would mean. Poly means more than one. Protic means more than one proton. Acids and bases are all about someone gaining or losing that extra proton. Right? So I just want to show you the definition here. See this guy H3PO4? It's an acid. And I can prove it's an acid by adding it to water and producing H3O+. The conjugate base byproduct that it makes is H2PO4. But check out this guy. This guy, I know, I'm almost done, Shirley, I'm almost done. This is my last slide. Okay, can you guys see how this H2PO4 is the byproduct of making this guy an acid? This thing right here is considered to be polyprotic because check this out. The byproduct that it produces can also react with water to produce even more acid and a secondary byproduct. And that secondary byproduct can also react with water to produce even more acid and a tertiary byproduct. And so what can actually happen in chemistry, and this is where it gets confusing, so I'm leaving this right till the end of the unit, but sometimes reactions don't happen all the way. And sometimes more than one reaction takes place. Here, this guy is going to create some of this, and some of this. But remember, this is all about a percentage. This guy might react 50% of the time. So you might have 50% this, and then 50% this. Right? But then this guy right here, which is now 50%, maybe it only reacts 30% of the time. So then of this 50%, 70% of it stays here, and 30% turns into this stuff. You just kind of get what I'm going here? And so what ends up happening is you probably have a lot of this and an equal amount of this. Then some of this stays, but the rest turns into this. Some of this stays, but turns into this. In theory, you could actually have a whole mess of stuff happening inside your beaker. You would probably have some of this, a lot of this, and you'd have a little bit of this, a little bit less of this, and even less of this one. So as a general rule, as these polyprotic things have their multiple reaction, each reaction is less than the previous one. That make sense? Okay, we're done. That was my last slide, right? Sweet. Okay, grade 12s, you guys can head out and check out the fair and I guess come back when you want. Grade 11s, I mean, we're done now, guys, so work on your assignments, your labs, work on whatever. Okay.